In this chapter, we are going to discuss three very important optical instruments. We start with human eye, that is the most amazing and extraordinary optical instrument. Then we will discuss about microscope and then telescope. Okay, the chapter as such is very simple to understand, very simple to retain it, and the problems also are of very simple nature. Okay, provided you keep it simple. Okay, if you fall in trap of formulas, then it becomes very confusing. Okay, so here we will try to understand basic things, the basic working, only the most basic things. Okay, the most basic principles, using as few formulas as possible. We will try to avoid formulas. Okay, as much as we can. We will only use the most basic formulas also. Okay, because if you start using formulas, then things become really confusing. Okay, okay, all right. So let's start with the human eye itself. Okay, human eye. Okay, human eye. Okay, few basic things, few important points about the human eye. It's like this: a normal human eye, a normal human eye can see objects clearly, okay, when they are placed between okay, least distance of clear or distinct vision. Okay, it is D and infinity. Okay, now what is this least distance of clear vision? If you have a normal eye, your eyes are normal, they do not have any defect, you are not using your spectacles, a normal human eye, then you can see objects which are kept anywhere. You can see objects which are at a very large distance. You can see stars, you can see moon. Okay, you can see objects located very far away. Okay, okay, and no matter what is the distance, you are able to see, but there is a minimum limit for that. Okay, so if this is the object, if this object is very at a large distance, I can see it very comfortably, I can see it clearly. But as the object starts to move closer to our eyes, we feel strain in our eyes. Okay, try to observe this. Try to observe the strain as the object moves closer, and if you are focusing on that object, okay, if you are trying to see it as clearly as you can, you will see that as the object comes closer, okay, at some point, okay, it starts to become indistinct. Okay, it does not remain distinct. Okay, so we have this minimum. This is kind of a limitation. Okay, it is a minimum distance at which the object should be kept. If the object is kept closer than that distance, then I cannot see it clearly. That distance is known as least distance of distinct vision. The symbol is D. Okay, okay, its value D is approximately equal to 25 centimeter. 25 centimeter. This is an average value. Different persons are going to have different distance. Now, okay, some may have more than this, some may have less than this. What it means is that if the object is kept closer than 25 centimeter, if the object is kept here, then I cannot see it clearly. To see the object clearly, it must be kept between this distance 25 centimeter and infinite, anywhere. Okay, at any distance more than or equal to 25. This distance is known as this least distance of distinct region. Now, these two distances, okay, this distance and this distance are also given a name. They are known as near point. They are known as near point, and this is known as far point. Near point and far point. Okay, so near point for a normal eye is equal to d, is equal to 25 centimeter, and far point is equal to infinity. Okay, now this simple fact itself is very amazing. Okay, let's see how. If you look at the structure of eye, the simplest possible structure of eye is like this. Okay, I have this spherical eyeball. Okay, in front of this spherical eyeball, we have a convex lens here. Okay, we are not going into all the details. Eye itself is a very complex organ. Okay, you can spend your lifetime studying and exploring eye itself, only eye. Okay, we are just looking at the most basic detail, most basic rudimentary details. Okay, I can represent my eye like this, simplest type of structure. I have this convex lens here, and this rear part is known as retina. Okay, where this lens makes its image, real image, and that image is analyzed by the brain, and that's how we see it. Okay, so this is the simplest structure. So what it says is that even if the object is at infinity, that means the light rays are coming parallel to this principal axis here. Okay, then I get my image at retina here. Okay, this becomes V. This is equal to V. U is infinity. Okay, and if my object is at this least distance D, then also I get the image at same position. Okay, this is my object here. This is my object. It is at D. This distance is D. Okay, then the image of this object also forms at retina. Now this itself is very amazing. Okay, it's very amazing. Why it is amazing? Here I have a convex lens. If I use this formula for the lens formula, 1 over V minus 1 over U is 1 over F. Okay, so 1 over V is equal to 1 over F plus 1 over U. If I change U, then this V should change. V should change. Okay, if I assume that focal length remains constant. But here with I, things are different. No matter where the object is, no matter what is the value of U, I always get image at the same position. How is that possible? How is that possible? Okay, it never happens that if you are looking at a close by object, then eyeball has certain size, and if you are looking at a further object, the eyeball becomes bigger. No, the size of eyeball remains same, no matter where you are looking. Okay, that means this image distance here, this image distance is same. Okay, that becomes possible by changing the focal length. So eye constantly keeps on changing its focal length. That becomes possible because of certain a set of muscles. They are known as ciliary muscles. That is part of biology. Okay, we are not going to go into that part. Okay, but it is just for information that the ciliary muscles are responsible to change the focal length of eye lens. It constantly keeps on changing depending on where you are focusing your eye at. Okay, this power of changing the focal length depending on the object is known as power of accommodation. Okay, let me write it here. Okay. For different object distance, image distance remains same. Image distance remains same. Okay, that becomes possible. That becomes possible by changing, okay, focal length or power of eye lens. Okay, and this property is given a name. This is called power of accommodation. Power of accommodation. Power of accommodation. The power of eye lens keeps on changing depending on the object distance. Okay. Power of accommodation. Now, can we find the range? In what range the power of eye changes? Okay, we can do it very easily. Let's do it through a problem. Okay, let's do it through a problem. Okay, the problem is like this. Question: diameter of eyeball is 2 centimeter. Okay, if the eye is normal, then find range of its power. We find the range of its power. In what range the power of eye lens changes? Can you find it? How can you find it? Okay, you can see your object at infinity. If the object is at infinity, you can see it clearly. If the object is at d, 25 centimeter, then also you can see clearly. Okay, so in these two extreme cases, you find what focal length is required. You know focal length, you know power. Okay, let's try to say this. Here, what is V? This is a convex lens here. Okay, I will write this 1 over F is 1 over V minus 1 over U. Okay, what is V? Okay, if we apply the sign convention here, this will be my sign convention. Okay, this is my sign convention here in both cases. Okay, we are going to use same sign convention throughout optics. Whatever sign convention we discussed in geometrical optics, exactly same sign convention we are going to use everywhere. Okay, we do not change our convention. We stick with one convention. We are following it all throughout. Okay, so this is my sign convention. Now this is the retina. This image is always created on the retina. Only then I can see it. Only then I can see it. Okay, here, so image distance, this is equal to diameter given 2 centimeter. This is 2 here plus 2 minus 1 over infinity. Okay, what do I get? I get focal length is plus 2 centimeter. What is power? Power corresponding to this focal length, it will be 1 over F. So 1 over 2 over 100, this becomes plus 50D. Plus 50 diopter. This is the power of eye. When I want to see the distant object, this is the power of my eye lens, 50 plus 50D. Okay, what is the power here? My object is kept here at a distance of 25 centimeter. This is 25 centimeter. Okay, what power is required such that I get an image here at the same point, at the same position? Okay, so here 1 over F is equal to 1 over plus 2. This remains same. Image distance remains same. Minus 1 over minus 25. Object distance will be negative. It is negative 25 centimeter. This will be equal to, it is 50 here, and this becomes 25 plus 2. Okay, so 27 over 50. Okay, so F is 50 over 27 centimeter. Focal length has changed. Earlier it was 2 centimeter. Now it has changed. It is less than 2 centimeter. Okay, what is power? Power is 1 over F. So 100 over 50 over 27. This becomes plus 54D. This is the range of the power. In this range, the power of eye changes between 50 and 50/40. Okay. Now this is for normal eye. Now if there is any defect in the eye, then things change. Okay. Hundreds of types of defects are possible in eye, but here, as far as physics is concerned, the basic physics is concerned, we are going to discuss two major and most common defect. Two most common defect in human eye. Okay, let's see. Let's discuss about those defects. Okay. Okay, let's see here. Okay, what we are going to do is we are going to discuss defects in eye. Okay, so two defects. First defect is myopia. Myopia, it is also known as nearsightedness. Nearsightedness. This is the first defect, myopia. Okay, let me write here also the second defect. Okay, the second defect is called hypermetropia. Hypermetropia. This is farsightedness. Okay, myopia, nearsightedness, hypermetropia, farsightedness. Okay, let's see what they are. Okay, let me write it point by point. Okay, the first point is near point changes. No, not near point, far point changes. Far point changes. Okay, and in this case, near point changes. Okay, you have to be very careful with the name. The name is nearsightedness. In this defect, this is a defect. In this defect, far point changes. What is the far point for a normal eye? Far point for a normal eye is infinity. I can see objects located anywhere. Okay, if my eyes are normal. If I have this defect, then my far point changes. Okay, now what it becomes? It comes closer to eyes. Closer to eyes. Okay, that is less than infinity. Less than infinity. Okay, let's discuss this one by one. Let's discuss this first. It comes closer. It can be few meters, it can be 1 meter, 2 meter, 3 meter. What it means? Let's say that I have this defect, myopia, and my far point has changed. It has become 2 meter. Let's say it is 2 meter. That means if an object is at a distance of more than 2 meter, I cannot see it clearly. I can see the object clearly if it is within 2 meters. Only then I can see it. That is the meaning of changing far point. Far point changes. Okay. Now, if you see what happens, okay, inside the eye, what happens, okay, in terms of physics, okay. So let's compare it with a normal eye. With a normal eye, okay. This is my normal eye. Normal eye. Okay. Now, in case of normal eye, okay, this is my lens. The object is at infinity. If the object is at infinity, I get my image right here at the retina, and then I can see it. normal eye. Okay. Now in defective eye, okay, if this is my eye, okay. Now if the object is at infinity, then the image is not formed at focus. It is formed in front of focus, something like this. This is where the image forms, and you have to remember this thing. In case of this defect, myopia, image forms in front of retina. To see the image clearly, the image must be at the retina. If the image is in front of retina or behind retina, in both cases, I cannot see it clearly. You will see the object. It's not that the object disappears or the image disappears. No, you will see the object, but you cannot see it clearly. You see it very blurred. Okay? It's because the image is not formed at retina, it is formed in front of retina. Okay? It's not that this happens for every object distance. No, there is a limit. What is the limit? That limit is this far point. Okay? What happens is, I cannot see the object at infinity. I cannot see this object at infinity, but I can see it if it is closer. Okay? So maybe if the object is here, then I can see it. Okay? Then the image forms right at the retina here. Okay? Then I can see it. Okay? This is my far point. If the object is beyond this, I cannot see it clearly. If the object is within this distance, then I can see it. Understood this? Okay? This is what is known as myopia, nearsightedness. I can see the nearby objects, but I cannot see the distant object. My sight, I have nearsightedness. I can see nearby things, I cannot see distant things. My sight is nearsighted. My vision is nearsighted. Okay. Now, how to correct it? Okay. I can see this object. I can see this object, but I cannot see this object. Okay? I cannot see this object. But if the object is located here at my far point, then I can see it clearly. And I want to correct it. What is the correction? Okay. What is the correction? Okay. So whatever is the problem is my correction. Okay. Whatever is the problem, the correction lies hidden in the problem. The solution, answer to any problem is in the problem itself. If you understand the problem, you understand you know the answer. Okay. It's like this. This object is very distant. I cannot see it. But if the object is here, then I can see it. Try to understand this very, very clearly. If you do not understand it, you will start looking for formulas, and then there is no formula. Okay, you will find many formulas in the books. Okay, but if you start falling in trap of formulas, life is going to be very difficult, very, very difficult. Okay, things are simple, provided you want to keep them simple. Otherwise, there is no limit to complexity. Things can become complex to any limit, and they can be made complex. Okay, here the purpose of this course is to simplify things, not to make complex unnecessarily. Okay, we never do that. Try to understand this. I cannot see this same object. I cannot see it at this distance, but I can see it at this distance. I can see the object if it is kept here. I cannot see it if it is here. what will I do? Okay, I will make use of a lens. I can make use of a lens such that if the object is here and my lens creates an image at this point, at the point where I can see it, then I will be able to see it. I cannot see an object at infinity. Let's say that my far point is 2 meter. My far point is 2 meter. If the object is at 2 meter, I can see it clearly. There is no problem. There is no problem. Okay. But I want to see an object which is kept at infinity. So what I will do, I will use a lens such that it makes an image. If the object is at infinity, that lens will make the image at 2 meter. And that I can see. Okay. And that is the correction. That is the correction. Okay. Now, so what is the correction? Correction. I'm going to draw it here itself. Now, object is at infinity. Object is at infinity. If somehow I can make its image here at this point, then I can see it. Okay. So I will use this concave lens here. Concave lens. Okay. So what we are actually doing is we trick our eyes. We trick our eyes. Now what this will do, what this lens will do is it will create an image here, a virtual image. A virtual image here at this point, where at my far point. Wherever is my far point, this concave lens will create a virtual image at that point. Now these light rays will enter our eyes. Now for the eye, for my eye, these light rays will appear to be coming from this point here. And if the object is here, I can see it clearly. Okay, so these light rays will be focused at the retina. Okay, and that's how I will be able to see it. Okay, are you able to understand it? Okay, so that is the correction. Now let's look at here, hypermetropia. In this case, near point changes. Okay, it recedes away from eyes. Okay, becomes more than 25 centimeter. That is D. Okay, a normal human eye can see an object if it is kept at 25 centimeter. This is 25 centimeter. Okay. In this defect, this far point recedes. That means if the object is kept before this point, I cannot see it. That is the meaning of near point. Normal person, near point is 25 centimeter. With this defect, near point recedes away. Let's say it becomes 50 centimeter. So if the object is at 25 centimeter, I cannot see it. And if I keep the object at 50 centimeter here, then I can see it. This is a defect. Suppose I want to read a book. I want to read newspaper. I will have to read it like this. How long can I read it? And do you think I can do this for a long time? For a few minutes maybe, but that's it. It becomes very uncomfortable. Apart from being uncomfortable, it is a defect in the first place. We need some correction. Okay. Let's see. Let's look at such a ray diagram. Okay. Normal eye. Okay. Here, if the object is at 25 centimeter. Okay. This is my eye. This is my object here. This distance is 25, equal to D. Okay. The image forms at retina. And that's how I see it clearly. In defective eye, okay, if the object is kept If the object is kept at D, object is here at D. This is my object. This distance is D. This I cannot see because image does not form on retina. Not on retina. Then where it forms? Okay, it forms away from retina like this. Away from retina. This is where the image forms, and this image I cannot see. I cannot see clearly. To see clearly, to see distinctly, I need my image at retina, not in front of it or not behind it. Okay, but it's not that this happens at all the distances. After some distance, okay, image starts forming at the retina. Okay, it's like this. It's like this. Here is my eyeball. Okay. Now, I cannot see this object here, which is kept at 25 centimeter. But if the object is kept a little further here, little further, okay, then this I can see just fine. This object I can see just fine. Okay, the image forms right at the retina here. This image I can see. Okay, this is known as my near point. Okay, this is near point for a normal person. Near point. This is far point. Okay, infinity is far point for a normal person, normal eye. In case of this defect, then the far point comes closer. In case of this defect, the near point recedes. Okay, if the object is kept here, I cannot see. I cannot see this. My eyes are defective. I have this defect. But if I keep the object here, then I can see. I can see this object, but I cannot see this object. But I want to see this object. Understand this? I can read book keeping it here. I can read book keeping it here at my near point. But I cannot read book keeping it here, 25 centimeter. But I want to read this book. I want to read this book. I cannot read this book. I can read the book if it is here. I cannot read it if it is here. What I will do? I will use a lens. Okay. I need to converge this a little bit. I need to converge the light rays a little bit. Here, I needed to diverge it a little bit to focus it on retina. Here, the rays are focused behind retina. I need to converge it a little bit. Okay. I cannot see my book here, okay, but I can see it here. So what I will do? I will use a lens. My object will be here. I want to read this. I will use a lens, such that the lens will create an image at far point here. Okay, the lens should create an image which is at my not far point, near point. If the object is here, I can see it. Object is here, I cannot see it, but I want to see it. I want to see it. I want to read my book, keeping it here. I will use a lens. So this lens will create the image of this book at my near point here. I will trick my eyes. The correction is all about tricking the eyes into believing that the light rays are coming from here, not here. So my object will be actually here. But I will trick my eyes into believing that the light rays are actually coming from here, not here. And then my eyes will be able to see that. Okay, that's what we do. Let's see. What is the correction? Okay, the correction lies here itself. Okay, what we do is we use a convex lens. Okay, I need to convert this a little bit. Okay. And what happens? Okay, the object should be between lens and focus. Okay, if I have this convex lens, this is my focus. This is my focus. Okay, and if the object is kept between focus and lens, then where is the image? Okay, the image forms like this. This is a focus here, and this is 2f here. Okay, that's how the image forms. Okay, a virtual image. A virtual image forms. The same thing we do here. Okay, so this distance will be smaller than focal length. Okay, so when the light rays pass through this, okay, in that case, the lens will make a virtual image like this here. A virtual image. A virtual image at this point here. Okay, let's see. See how we trick our eyes. Okay, how we trick our eyes. Okay, we trick our eyes into believing okay, I think I need to make this diagram. Okay, anyway, note it down. I'm going to make this again. I'm going to make this again. Okay, it's like this, the correction. Okay, the correction part. This is my lens. Okay, I cannot see my object here. This is my object, this distance is d. This object I cannot see because it is focusing behind the retina. What I will do is I will make use of a convex lens. A convex lens. Now what this lens will do, is it will create a virtual image here where at my near point. At my near point. Okay, so to the eyes, to my eyes here, okay, these light rays will seem to be coming from here, which is my near point, and that I can see, Okay, so this is how we correct it, and this is just it. That's it. Okay, no further theory is required. Let's start doing the problems. Okay, straight away. A person cannot see objects clearly beyond 5 meters. Beyond 5 meters. Okay. What is required power of corrective lens? Okay. Next one. A person cannot see objects clearly, okay, nearer than 1 meter. Nearer than 1 meter. Okay. What corrective lens is required such that he can read a book comfortably? Okay, look at this. And then one more. A person uses bifocals of powers powers plus 2d and minus 0.4d. Okay, what are is near and far points. Okay, let's do this few simple problems. Okay, from this topic only such type of simple problems are asked. Okay, there is no scope of complicating it. Okay, still there is a scope of confusing it, make it confusing. But if you know the concept well, okay, you will never be confused. Okay, if you decide to keep it simple, you will never be confused. You become confused only when you decide to make it difficult, when you decide to make it complex unnecessarily. Then you will start getting confused. Okay, do not make it difficult. Do not make it unnecessarily complex. Things are easy, keep them easy. That's it. Okay, first problem. I cannot see an object which is beyond 5 meters. Okay, I can see this object clearly, this clearly. Okay, but if something is at a distance more than 5 meters, that I cannot see. Okay, I want to normalize my vision. I want to correct this defect. What type of defect it is? Okay, I cannot see distant object. If the object is at a larger distance, I cannot see it. That means my far point has changed. Ideally, my far point should be infinity. I should be able to see any object kept anywhere. Okay, my far point should be infinity, but now it has become 5 meters. Far point has changed in this first problem. Far point has changed. Okay, it is myopia. Okay, it is nearsightedness. Okay, do not be confused with these conflicting words here. Here I am saying that my far point has changed, and here I am saying that this defect is nearsightedness. The meaning of nearsightedness is I can see nearby objects, I cannot see the far off objects. That is nearsightedness. Okay, now how to correct it? I can see an object at 5 meters. I cannot see an object at infinity. I want to see object at infinity. What will I do? I will make use of a lens. Which creates the object at infinity, the image of that object at infinity. If it is created at 5 meters, then I will be able to see that. Okay, you understand this? Okay, so it's like this. Okay, again I am explaining this again. Okay, so that the things become clear. Okay, this I can see. This is 5 meters. I can see. My eye is defective, but I can see this at 5 meters. Okay. This I cannot see. This I cannot see. What do? I make correction. I make use of lens. Now, what type of lens? How will what my lens should be? My lens should be such that, okay, what correction I need? I need to see this object. I need to see this. I want to see this. Okay, and I need some lens for this correction. Okay. Now, so this is my object at infinity here. Infinity. Okay. If I do not use any lens, it is going to converge here. Okay. But if I make use of a diverging lens here, then this diverging lens will create a virtual image here at my far point. Okay, so my eyes will be tricked. My eyes are going to be tricked. My eyes will think. My eyes will think that this ray is actually coming from here, and this is something that I can see. So the eyes start to see, and that's how we see. Okay, and that's what the correction is. Okay, so what do I need? I need this. I need this. Object is infinity. I want my image at minus 5 meter. Okay, I want to find focal length. That's it. Okay, so 1 over focal length. Okay, so object at infinity. Object at infinity. Image at 5 meter. What is focal length? 5 meter. I don't even have to calculate it, but if you want it, you can calculate 1 over v minus 1 over u. 1 over minus 5 minus 1 over infinity. Focal length is minus 5 meter. Okay. Focal length will be minus 5 meter. Okay. So what will be power? Minus of 1 over there. Minus 0.2 diopter. Minus 0.2 diopter. Okay. You understand this? Okay. Try the next one. It is similar to this. Absolutely similar. Okay. Now next one. Okay, a person cannot see objects clearly nearer than 1 meter. Object is here, I cannot see. It is here, I cannot see. Here I cannot see. Here I cannot see. If it is beyond 1 meter, then I can see. I cannot read my book from here, not from here, not from here. But if it is here, at 1 meter distance, I can read it. What has happened? My near point has changed. The second problem, near point has changed. Near point has changed. Near point has changed. Okay, it is hypermetropia. Okay, it is farsightedness. It is farsightedness. Okay, how do we correct it? So let's look at the problem. Okay, let's look at a normal eye. Okay, normal eye, 25 centimeter. This is 1 meter. Okay, so this is the problem here. This is the problem. Okay, if my object is at 1 meter, if my object is at 1 meter, I can see it. Okay, if this thing is an object, this is 1 meter, then my image forms the image, my eyes form the image just fine at the retina here. Here, I am able to see it. The problem happens if this distance decreases. Okay, if the distance becomes 25 centimeter, that is D, then there is a problem. Okay, now if the object is kept here, this object, at what distance? At D, 25 centimeter. Now this I cannot see. Okay, now this it will be focused behind the retina. Okay, this I cannot see. Okay, then what is the correction? What is the correction? I am going to trick my eyes into believing. Because what I will do is, I want to see this object. I want to see it. I cannot see it. I want to see it. So I will trick my eyes using a convex lens. Okay, I need to converge these rays a little bit. If I converge it a little bit, it will be focused here at the retina. Okay, so what I will do for that? Okay, if I like, I will keep my object here at 25 centimeter. I will keep my object here, but now I will use a convex lens. Now this convex lens, okay, will create a virtual image here, a virtual image like this. Now the eye will think Okay, the eye will think that this light ray is coming from this point, which is my near point. So that's fine. Let me see it. Okay, then the eyes will start seeing it. Okay, that's how it triggered. Okay, into believing that the light rays are coming from a nice point. That is my near point. This is my near point. My near point has receded. Okay. Now, so what I want? My object is kept here. I want my image here. What is this image? Where should be the image? It is 1 meter. Okay. What should be focal length? 1 over f, 1 over v minus 1 over u. 1 over minus 100, minus 1 over minus 25. This is 100 here, minus 1 plus, this is 4. Minus 1. Okay, that's fine. U and V both are negative here. Okay, so this is minus 1 plus 4. Okay, that's fine. So F will be 100 plus 100 over 3 centimeter. It will be plus 1 over 3 meter. Okay, so what will be power? 1 over F. It is plus 3D. Plus 3D. Okay. Try to understand. We are not using any new formula, no new formulas. Okay. If you refer to any other resource, there are formulas. Case by case formulas are given. Okay. Do not fall in trap of formulas. Okay. You will be left wondering. You will go nowhere. You will go nowhere. Formulas are essential. They are important. But only where they are required. Not everywhere. If you start looking for formulas for every case, then there will be millions of formulas. How many do you think you can remember? And for how long? Not much. Okay? So it's important to remove your dependence from the formulas. Okay? Understand the basics, and that's what is required, not the formulas. Formulas are not required in this case. We can do it using simple lens formula, the basic formula. That's it. Okay. Now the next one. Can you try the next one? Can you try the next one? Bifocal. Okay, some people have both defects, hypermetropia, myopia, both. They need to use both types of lenses to correct both visions. Okay, so one person here, he is using this bifocals of powers, 2 powers are given here. Now you will have to recognize which lens is for which defect. Okay. Then it becomes easier to solve. Which lens is for which defect. Okay. So we use convex lens. Okay. Convex lens. I have these 2 powers here. Okay. These 2 powers here. Plus 2D and minus 0.4D. Okay. Now this is for farsightedness. Near point has changed. And this is for nearsightedness. Okay. Here far point has changed. I can see nearby objects. I cannot see far off objects. My far point has changed. I can see far off objects. I can see moon clearly. But I cannot read a book. I use convex lens. Okay. So if you are a student watching this lecture and just in case you happen to be using spectacles, then the chances are very high chances that you are using a lens of negative power. This type of defect usually happens in young ages. Students like you, in case you happen to use one, okay. This generally appear in older ages. Okay, so if an aged person is using spectacles to correct his vision, chances are most probably that person is using a convex lens, a positive power. Okay, a general thing, general, most common things. Okay. Of course, any kind of disease defect can happen to anybody at any age. Okay, there is no control. Okay, okay, there is okay. You understand that. Anyway, so the person is using these corrections. Near point has changed. Okay, it should have been 25 centimeter, but it's not. Okay, here it should have been infinity, but it's not. Okay, now how do I find the near point? That means this person cannot see object which is kept at 25 centimeter. To correct that, the person is using this lens. Okay, that means the near point has shifted. The object is kept at 25 centimeter, but its image is formed somewhere else. Okay, and that image the eyes of the person see. Okay, so here U is minus 25 centimeter. Okay. Okay. What will be power? Okay. What is focus? Focus is 1 over P. So 1 over 2 plus 1 over 2 meter. It is plus 50 centimeter. I want to find V. Okay. This will be my near point. This will be my near point. Okay. So let's find it. 1 over F is 1 over V minus 1 over U. Okay. So 1 over V is 1 over F plus 1 over U. Okay, so 1 over plus 50 minus 25. Okay, makes sense? Plus 50 centimeter. This is minus 25 centimeter. This is 50 here. 1 plus 2. Okay, so what is V? V is 50 over 3 centimeter. Is that possible? It should have been 25 centimeter. So object is kept at here 25 centimeter. Okay, and okay, no. This is a plus here. It should be plus here. So this will become minus. Okay. So V is minus 50 centimeter. Okay. So this is my near point. Near point is 50 centimeter. It should have been 25, but it is not. It is actually 50. To correct that, I am using this lens. Okay. Now here, that means U is minus U is infinity. Okay. Focal length is equal to, this is power. Okay. 1 over P minus 1 over 0.4. This is minus 2.5 meter. Is minus 250 centimeter. This is the focal length of this lens here. Okay. V I do not know. My far point will be V. My object is at infinity. I am using this lens to see that object. So wherever the image is formed, that becomes my far point. Okay. So 1 over V is 1 over F plus 1 over U. Okay, so this is 1 over minus 2.5 meter plus 1 over infinity. Okay, so V becomes minus 2.5 meter. Okay, that means this is my far point. This is 2.5 meter. If the object is beyond 2.5 meter, I cannot see that. To correct that, I am using this corrective lenses. Okay. In problem sheet, you will find some interesting problem. Okay, very interesting problems from this simple topic itself. Very interesting problems in problem sheet. Okay, and we will discuss that also during discussion. Okay, so that's it for eyes. Okay, next class we are going to study microscope.